Uh, Unfortunately, it does. I'm giving some. I'm going to try to present something today, but unfortunately, even 4 weeks doesn't make me feel any more prepared.
No. Okay.
Yeah, I know it can be that way.
Was the seminar that you attended, Dr. Sobchak, on it was on geometric algebra? Was it successful? Interesting?
Well, it was an interesting meeting. A lot of interesting speakers on neural networks, applications. It wasn't so much pure mathematics. Dr. Hestenes was there, who's the star speaker, talked about Dirac theory of the electron and his, in particular, I don't know if you're aware of this constant beta that arises in the Dirac theory of the electron, but he was talking about that when I was a graduate student back in 1965, and he seems to have found out what it is. He thinks it's very important, the discovery that he's made. So that was pretty interesting talk he gave.
Ah.
Have you heard about this beta in the Dirac equation? Have you looked at that?
Not in detail. I mean, I'm familiar with with the fact that there is a Dirac matrix called beta, right? That.
Well, it was an interesting talk. Basically, he believes the electron takes a helical orbit at the speed of light, so it circles up with the so-called Zitterberg-Wagen frequency. So I quoted Einstein as saying, if one can understand even exactly the structure of an electron, that would be a great accomplishment. That was the motivation of his research over the last 60 years, I guess it comes out to. So yes. It was, but they had other talks about, for example, Bézier approximation of surfaces, which I found a guy named Rockwood, gave a talk about Bézier approximations to surfaces, and a bunch of talks about neural networks, progress in neural networks. There were a total of about 30 or 35 people attending in presence in Denver, and about another 30 people on virtual, which of course is what I was participating in, virtual. So it was the first meeting of this series, so we'll see whether it continues in the future.
So, I mean, we're usually thinking of Clifford algebra as an abstract mathematical subject, or at most sort of applicable to physics, but I know that there was quite a movement towards using it as a tool in robotics and in the sort of the computational aspects of movement and so forth, which
Oh yes, robotics was big at the conference as well. In fact, I would say that Clifford algebra, geometric algebra, is more recognized in that group of people than in mathematics. I still think there's many mathematicians that probably don't even know what a Clifford algebra is. What do you think, Dr. Cruz?
About this idea of use Clifford algebra in robotics.
Yeah, I guess there are people at FESC that were interested in Clifford algebra. A number of people actually.
I saw recently an video in YouTube that speaks about the use of quaternions and octonions in robotics. and the presentation claims that the operations of transformation is more are faster than the ordinary calculations. Then they claim that the people in robotics and computer science are using intensively the octonion, quaternion algebras, and of course Clifford algebra. Yes, I think it is too much interesting. By the way, I saw another, but this was about quantum computing. And in quantum computing, they presented via a states machine. What is the difference between ordinary computation or classical computation and quantum computation? And they present in the state machines via a graph. Graph
That's right. Lattice theory.
Yes, how this, what are the difference between these two kinds of calculations? I think that it is very interesting because I think that this connects with the algebra of quaternions, octonions, and so on. Or maybe in more general way with a Grassmann algebra in general.
Yeah, there were a couple of talks on quantum computing as well. So it was really financed by, I guess, some of these big companies that are working in such areas like that. It was an interesting conference just to see the applications of geometric algebra, Clifford algebra. It seems like this group is the biggest in the world that's working on it. Pure mathematicians, you know, Grassmann algebra comes up in differential forms and used by various mathematicians in related areas, but they don't consider it the generalization of the real number system as I do, and some other people. But I think it should be, someday it'll be recognized that way. That was what I tried to emphasize in my talk, that it really should have been recognized in the 19th century as a generalization of the real concept. It's really equivalent to linear algebra. It's just another way of looking at a linear algebra with a matrix representing a geometric number or Clifford number, a coordinate matrix. Every matrix can be thought of as representing a number of different geometric numbers or Clifford algebras. They're all isomorphic, really, to matrix algebras, finite dimensional.
But the concept of quaternion is an old idea, right? Hamilton, understood this abstractly, and it wasn't very long after that there were quite a large number of people who were very interested in using quaternions geometrically, right, to represent torsion or screw motion and so forth.
Well, actually, they're still talking about that. That was brought up many times in this conference.
But this is strange to me because it's kind of like, why are we still talking about this? Because it seems that this was really fundamentally understood by people like Hamilton at that time.
Well, the
But
interesting
there
thing
was a strange history, though, that the early days of electromagnetism were actually expressed in quaternions, right? And that it wasn't until later that the vector formalism became more popular. And
well, that's
somehow,
right, Heaviside.
but the quaternion formulation actually came first, and so the idea that we can apply like Clifford algebra as in a generalization it seems very natural. Like it was and so it seems strange that this is still so. I mean, still unapplied, right? So.
What caught my attention was that actually the name of the Cayley-Hamilton theorem, Hamilton's
Yeah.
name applied to it, and actually he proved it with quaternions. It was, and Cayley actually proved it in dimensions 2 and 3, but it wasn't until Frobenius in 1878 that proved the general Cayley-Hamilton theorem using matrices. So it was first proved by Hamilton in using quaternions, which was pretty strange to me. I hadn't realized that was why it was called the Cayley-Hamilton theorem.
There was another talk by Dr. Kaufman. I saw they have a seminar similar to us, and I don't remember the name of the seminar, but as this is in knots and entanglements, and in this seminar, he presented this theory of Cayley and Hamilton, how we can go from Clifford to quaternions to octonions, and he says that there are many people working in that in this theory that are trying to build new algebras from this. Then I think that this is an interesting way for approaching this kind of problems. Yes, and about the idea of rotations, he connected with the concept, this idea of Dirac, about the belt of Dirac that is used for showing how the rotations can be expressed in terms of, I don't remember exactly, in terms of quaternions, and then all the operations of rotations are more easy to represent in this way. Then it is interesting subject. I think that maybe this can be explored more intensively.
Dr. Sobczak, your current sort of interest to me still seems focused in a somewhat unusual direction, right? Saying that that you look at the geometric algebra as a kind of representation of matrix algebra, right? That
exactly. Yeah, matrix algebra is a coordinate matrix of a geometric number, or Clifford algebra.
Well, so it's in a sense taking the notion of matrix algebra as the kind of the mother algebra, and then geometric algebra as a kind of way of representing it in full generality, right? That I mean that the idea that you don't lose anything by going to Clifford algebra, that
that's right.
is kind of new, because one would generally think of Clifford algebra as being a subset, in a sense, of matrix algebra. That it doesn't require the full generality of the structure of matrix algebra. That you so you normally think of matrix algebra as representing Clifford algebra, not the other way around. But so I haven't quite fully understood this yet from your presentation. But it also, you also brought in this notion connected with Grassmann algebras of dual or compatible Grassmann algebras.
Yeah, I think that's the key idea, really, that matrix algebra is reduced to anti-commutivity and idempotence. Well, all of which can be represented in terms of null vectors or algebraic quantities which have square 0. Of course, normally we don't think about a vector as having square 0, but well, that's like an inner product. But that's the thing. If you take two Grassmann algebras, they can fit together very nicely and give you any matrix algebra, really.
Let me show you sort of the paper that started me, that made me interested in Frobenius algebras. And in particular, this was in reference to the notion that arises in relativity, of observer, like understanding what an observer is. This came a little bit later, but the beginning was actually a paper with the primary author is Dr. Cruz. Let me just show you this one. I'm sure you'll remember this paper, Jesus.
Yes, I remember. Yes.
Yeah, let me just clean up my screen here. Take this over here.
I don't even know what a Nijhouse-Richardson algebra is, actually. I wonder if it's related to a Frobenius algebra, or what's the difference? I don't know.
Yes, it is. In the I'm going to sort of stumble through this in various ways, but this ultimately led me to do a lot of calculations in computer algebra in support of a question that was raised at the end of this paper. But one of the let's just skip to the contents here.
Okay.
So I think one of the applications of this Nijhouse-Richardson algebra was to electromagnetism. There was another paper specifically on electromagnetism using this formalism. In really brief and sort of probably too brief a form, this algebra is really Lie algebra, but with the notion of derivations as an integral part of it. So it's non-associative in the same sense that Lie algebra is non-associative, and the whole point of this algebra is to define the brackets analogous to Lie brackets, which describe the structure of this non-associative algebra, and the non-associative algebra includes derivatives, right? So it's kind of like taking Grassmann algebra and then adding derivations, and you also get the dual structure from the dual linear algebra.
I see the Bianchi identity in there too is interesting.
Yeah, I remember that the Professor Olszewski used to present this problem, asking about if one derivation of degree larger than 1 is a derivation. And then it can be demonstrated easily that this is not a derivation. And then this requires a Lie bracket, and a Lie bracket is the way that we can a generalization of the derivation to multigrade algebras.
So yeah, this interesting Frobenius algebra of two idempotents. Well,
Yes,
I can think of that's
where we're
interesting.
going. That's what we had to get to. So let me just skip down to this section, right? So the fundamental idea of Frobenius algebra is you take any algebra and then add a scalar product, but you require that this scalar product be associative in a very specific sense, so that the elements of the algebra how should I say this? Maybe this is actually presented in a more algebraic way, but there's actually a better way to write this graphically. I just skip ahead here, and I'm not sure if he writes this easily or not. No, in this particular paper, the emphasis is more abstract. Let me take one more paper. Sorry, just find the right place here. This is not it. Oops. One moment here. Darn.
I'm wondering why Frobenius didn't do more with Clifford or with Cayley, and with Clifford algebra even.
Just one moment here. I'll find my way here in a minute. Okay.
Maybe it's in the paper that you and Professor Shevik write, where there are many graphical representation of these algebras.
Yes. There are several places I could go here to. Unfortunately, I had a set of web pages here now. Now they seem to be not where I expected to find them.
Wait a moment, maybe.
Yeah, I have another one here.
Can a Frobenius algebra be represented by a matrix algebra in any way?
Perhaps not in general. Here's a better picture.
Like a Frobenius algebra with two idempotents. That's interesting. How many elements does that Frobenius algebra have? Does it have a finite number of elements? Well, I guess they're all infinite, but of bases.
Well, the generators, the dimension of the Frobenius algebra is 1 plus n squared, where n is the number of number of primitive idempotents. Yes.
Okay, well that's interesting because.
Let me just. I'm looking for a specific picture that not there. Yes. Okay. This is one particular picture. Let's see.
Okay.
Let me. There are several ways to write this, but basically, associativity means that we can. Come on. I know it's in here somewhere. Let me just. Dr. Suptek, you're familiar with Oshevich's work on operas in general, right?
Yes, yes. This is a representation of operas of category theory. Yes, yes. We need to read from top to bottom and from left to right. Yes.
I'm sorry, I'm struggling with this. There is one particular graphic that I know it's here somewhere. Yeah, these are not the right ones. Okay. There. Okay, maybe that's a good diagram to actually discuss. So the concept of associativity implies that we can, if we have three elements of the algebra, we can multiply the elements of the algebra to get a new element of the algebra and then take its scalar product with a third, or we can do it in the other grouping. We can take the last two and multiply them and then take the scalar product with the first, and these are equal, right? So that's associativity of the scalar product. And in addition to that, an algebra is Frobenius if the scalar product is non-degenerate, right? So the fact that the scalar product is non-degenerate is what produces a kind of duality called the co-algebra. And so it means that we can basically invert the scalar product.
Okay, that's interesting.
But when we're looking at this diagram, the multiplication in the algebra is written like a upside down fork, right? So each vertical line is an element of the algebra, or maybe it's better just to think of them as vectors, right? So and when these lines meet, it's some operation on the vectors. Yeah. So
then I remember that the vertical lines are tensor product, a tensor product, and then when we find a dot or intersection between lines, there is a process. Then the process maybe can be a multiplication, for example, or plus operation or something like this. Then this is the idea in this representation. And in image that we can see now, we are seeing first multiplications. I am speaking in the right size of this picture.
Yes.
And in the right size of this picture, we have multiplications, and is coming with this multiplication at is tensor product with identity. But after we have an operation that is an annihilation, that is equivalent to this scalar product here. Then this is, I think, the idea represented in this picture.
But the just to, okay, let's skip back to this paper, because here you see where we have this symbol looks like a Y, right? That's the same symbol as in the previous diagram, right? It's just
Yes.
in the language that Oshevich wanted to promote, this graphical language, he called this a letter in the language. But the important part of the language was that it was not linear, wasn't just sequential. Instead, we compose these letters by a process he called grafting, right? So that we would think of this symbol that looks like the Y as having a process with two inputs and one output, and we can compose these processes. If we have two of these, we can compose them in at least two different ways, right? So we can take the output and feed it into the input of a second one, right? And then we end up with a process that has three inputs and still only one output, right? Because we've composed this letter with itself, right? And now, and this process continues because the second letter here, epsilon, is equivalent to the notion of a form, a one form, so that if we evaluate the vector by a one form, then we get a scalar. And the notion in Frobenius algebra, well, Frobenius algebra has a large number of different equivalent definitions, but the definition that Ishevich found most useful was to consider the Frobenius algebra as given by something called the Frobenius form. And this Frobenius form can be expressed as a one form evaluating a 2-1 tensor, in effect, right? So that you get, and I didn't draw this diagram here easily, but the point is that if you have a multiplication in your algebra, and you have one form. A one form is something that you can graft onto the multiplication, so that you get a process that has a single input, two inputs, and then no outputs. So skipping back here again. So this lower part of the diagram is representing this process of a scalar product, but we want to we decompose this into two parts, so that how should I do this?
Yeah, it looks like you're subtracting the scalar part to get that on the left or something.
Well, we don't have a notion of scalar part, but we have the notion of a form. So we can take any element of the algebra and apply this form to get a scalar. But there's a distinguished, really important form that is called a trace, right? So that if we how should I do this? I don't know if I have any more diagrams in here like this. No.
Okay, can kill
I don't.
trace.
I'm sorry. There's the paper that. Yeah, let me check if this is here. No, it's not in that one. Well, we can get into this a little bit more because this is all later, because this is all related to this whole notion of the operad calculus, right? But let me skip to one statement. I think it was in here. I forgot. Yes, this was the reference to just a very quick reference, and the first one that I saw, although it's not the first paper in which Oshevich mentioned this idea, but the idea that Clifford algebra is necessarily a Frobenius algebra that obeys a particular axiom, right? And that this axiom can be expressed graphically as a grafting of a co-multiplication with a multiplication. So the co-multiplication structure comes from the Frobenius algebra. This
maybe in this picture again, we have a co-multiplication and one multiplication in the left right. Excuse me, in the left side, and then we have an operation here that is to contract one element that is in the coproduct with the elements that are in the products. And this is equivalent to a contraction. Then here I think that is only saying the commutative law in this kind of operations that are symbolically represented, but the cross that is in the middle. Then I think that we have two operations here that are co-multiplications that is from Frobenius algebra and a multiplications. And then with this, we are building different kinds of elements. And I think that in the R row lower says Frobenius algebra were unary handle. And this is important because this is related with the notion of antipode later. Then I think that we can understand these graphs in this way. Excuse me, I interrupted.
No, I appreciate your comment. Maybe I say one more thing in preparation before I start showing you the part that really I understand better, and that was what I actually did in computer algebra to actually explore this. It was always in context of a paper that was written by Oshevich, but he had some trouble with the algebra, not difficulty, just so much that the fact that the algebra ended up being rather complicated. Many pages of calculations, which in computer algebra system you can actually accomplish very quickly, and extend generally the calculations to higher dimensions. But there was one more paper, and it's fairly relevant to our discussion. Right? This paper was, I think, referred to by Dr. Sobchak about a month ago as one of the papers that Oshevich wrote specifically about the relationship between Clifford algebra and Frobenius algebra. And it's using this formalism, the graphical formalism, to explore the notion that it's like put really simple terms. If you have an element of a Clifford algebra, you can take the scalar part of it. That's a common operation, but Oshevich was concerned that this operation of taking the scalar part was somewhat arbitrary, right? That an element, he didn't want to consider that the elements of the Clifford algebra should necessarily be determined by their grades. So this notion of the Frobenius algebra was so it arises naturally in Clifford algebra because you have this notion of being able to take the scalar part, or the order zero part of a Clifford number. But the question what arises is that the only way, right? I mean, is that the only thing that you can do? Is the only thing you can do to a Clifford element to get a scalar from an arbitrary Clifford element? And the answer, at least from the point of view of the Frobenius structure, is no. Like there are many possible ways to define a Frobenius algebra on top of a Clifford algebra, provided that you're willing to specify some form. In order to get this scalar part, you can take ordinary Clifford multiplication and then use the form to get the scalar part. But the structure of this form is somewhat arbitrary, at least in general Frobenius algebras. But in the case of the Clifford algebra, it always comes down to what Oshevich called the Killing-Cartan trace, right? Which is just basically the trace operation. There's something rather special about this trace. And this paper went to a lot of length to consider all the different possible ways in which you could express the notion of trace. Or at least generalize, maybe it's better to say how you could generalize this notion of trace. And algebraically, you can actually compute this for small numbers, for your algebras of small numbers of generators. But ultimately, the conclusion was, at least in this paper, was that there's really only one good way of defining this trace, and it's the way it's always been done in Clifford algebra. But this was also part of a program that Oshevich had to ask the question of, well, given that we have basically just one way to make Clifford algebra into a Frobenius algebra, that means that with every Clifford algebra, we actually have a natural co-algebra structure. But yet we don't see the co-algebra structure actually being applied in physics. And it was always sort of a question, well, why isn't there some physical meaning associated with this co-algebraic structure?
I remember that Professor Osiewicz likes to speak in this way about the creation operation. Then, for example, in one particular, if one particular is decaying in another two, is similar to the coproduct in this in algebra. Is similar to coproducts in algebra because from this. And I think that what we can find different examples in particular physics that are expressed in good way in operation of coproduct.
Well, coproduct is like being basically just an upside down multiplication. It means that we have a process that has two inputs and one output, right? And these, whether these inputs have anything specifically to do with particles or not is kind of a somewhat different question, I think. So the co-product is like we have a single input and we end up with two. So you were suggesting that this is somehow associated with creation?
Elementary property in a co-algebra, the co-product, because this is needed for building a co-algebra. Then, because I use it as example in this idea.
But consider, for example, that you have just an arbitrary element of the Clifford algebra. It could be a vector or a bivector, etc. And then you ask the question, is there some unique way that I can take this single element and make two elements out of it? Right?
For example, a particle and an antiparticle creation.
Mhm.
I think that this can be modulated in this way. I don't remember too many examples of this that Professor had been used, but I think that it can be made if one look examples in particular physics.
Well, the notion of creation and annihilation operators arises in Mashevich's work a little bit differently, right? He would associate creation with the exterior product, right? With the mapping, with the operator that comes from the application of the exterior product. But
So that's an interesting. Yeah, where he's saying that each a priori, each Clifford algebra is a Frobenius algebra in many ways. That's an interesting statement there.
yeah, so it's not uniquely Frobenius, but the argument is that it's a pretty loose argument that the only useful way of defining a Frobenius, associating a Frobenius algebra with the Clifford algebra, there is only one useful way.
Yeah, so it looks like Frobenius was interested in just generalizing somehow, rather than really doing anything with Clifford algebra, generalizing it to his Frobenius algebra or something. Just trying to understand.
Well, the point of the Frobenius algebra was to understand the duality, right, between algebra and coalgebra. But in the context of the other duality that's associated with linear algebra itself, right, with the dual linear space, so that you actually get like four different, well, two different types of duality, right? Wow, this goes
No,
on.
that's interesting. Trying to understand, getting into the mind of 19th century mathematicians, what they're thinking about. I guess it's been generalized many times now, of course.
Well, Frobenius algebra became especially interesting when it was clear that they had applications in topological field theory in quantum mechanics.
Yeah, so it looks like Gibbs Heaviside is what really changed the direction as far as engineers and other scientists are concerned. They left all this abstraction and just concentrated on the Gibbs Heaviside algebra, which was very adequate at the time, except for Einstein, of course, needed a more powerful algebra than just Clifford, than Gibbs Heaviside. Although Bill Bayliss has done a lot with, well, algebra G3. He does everything with relativity theory for just the geometric algebra of Euclidean space. He gets special relativity and talks about it in terms of that. It's slightly more general than just quaternions. Well, it's like Gibbs Heaviside plus quaternions. That's, the even subalgebra of the Euclidean geometric algebra, 3 dimensions, is isomorphic to the quaternions. Thinking about quaternions as being bivectors in Euclidean geometric algebra 3 space.
But nobody seems to be interested in asking the question of what's the natural coalgebra for quaternions, for example, right? Like, so we know how to multiply two quaternions. So and we have a natural Frobenius structure that arises in the same way as it does for Clifford algebra. So that that means that there is a coalgebra structure associated with quaternions as well, which doesn't have any immediate obvious engineering applications.
No, maybe
But
that's worth pursuing a little bit more. Exactly, just studying it in terms of the coalgebra of the quaternion algebra, or the geometric algebra of 3 dimensions. What is the coalgebra of the geometric algebra of 3 dimensions, which contains quaternions and gives Heaviside vectors, really?
So, some of this was explored by Abramovich and
Abramovich.
yeah, in Cooperstown, I think, and Fauser. Fauser was a student of Oshevich's, and Abramovich and Fauser worked together on producing computer algebra.
Fauser was a student of Oshevich?
Yes.
I didn't know that, actually.
Yeah, I haven't heard much from Fauser lately, but there's a reference here to an early paper by Fauser. Let's just skip down there.
Yeah, it looks like I dropped out for a second. I didn't know that Fauser was a student of Oshevich.
Yeah. Most of Fauser's work was on something, a related subject called Hopf algebras, but that's another story altogether.
Yeah, well, that's another. That's right.
In any case, okay, I'm floundering around here, and what I really, I guess, wanted to show you was that after trying to understand this work that Oshevich was doing and trying to assist with the calculations, I eventually started using a computer algebra package called Axiom. You know, most of the rest of what I can tell you about that is not very much about mathematics, but more about computer algebra systems in general. Axiom is a computer algebra system that was developed by IBM in the sort of periods of 1970s, 1980s. But it never became a commercial product as such. And at some point, the research project, which had been going on quite aggressively in IBM for a number of years, lost its funding. And so the Axiom system never was marketed in the same way that these days we see Maple and Mathematica. But the history of computer algebra goes back to the late 60s and early 70s. And the work that was done at that time, in some ways, is still quite competitive with the commercial, what the computer algebra that's become available commercially. So I did quite a lot of work with what's called open source software. That is software that was formerly commercial or formerly research-oriented software that was just made publicly available, and people could use this open source software however they saw fit. I mean, basically, I mean, there are some limitations in the release of this software, but they're very general, and you could incorporate this into other systems and so forth. And I became involved in the sort of, I guess, the 1990s or so with the people who were making Axiom available as open source software, whereas formerly it had just been a research project at IBM, and very short time it was actually marketed by a company called NAG in Europe, um, the numerical algorithms group. And the numerical algorithms people wanted something that could do computer algebra in addition to just doing numerical calculations. So they tried to market it as a competitor to Maple, but at the time it was, I think the whole market was unclear how important this would eventually become and so forth, and so they stopped its commercial development. And then so the version that became the open source Axiom in about the year 2000 or so, 2001, was actually the version that was briefly marketed by the numerical algorithms group, but they how should I put this? It was just a huge amount of work. Like the work that IBM had invested in this, amounted to hundreds of man years of effort, and it was in contrast to another branch of computer algebra development that was actually based on a system called Maxima. And what we see today is Maple and Mathematica are kind of descendants of this Maxima software that was also developed roughly about the same time. But they were developed with very different orientations. Both of these packages are written using Lisp. You might have heard of the Lisp programming language. It was developed in 1960s and as a programming language specifically oriented for manipulating symbols, and as opposed to doing numerical computation. So it was the orientation was, how do you represent a formula and manipulate this formula in a sensible way. The tack that was taken by the Axiom people was to actually apply formal mathematics, right? They wanted the computer algebra system to be fundamentally algebraic, like so that it was the notions from universal algebra and from abstract algebra and also from category theory, all provided a way of formalizing mathematics as a separate concept, as a fundamentally sort of algebraic concept, and this was contrasted with the kind of manipulation of symbols that was implemented by systems like Maxima, which just said, there are certain operations we can perform on these symbols, and these operations, if we do them in a certain way, they will correspond to the mathematics. It can be made to correspond to doing manipulations in mathematics. Whereas in the Axiom case, one started out with the mathematical properties first, and then had to build the necessary mathematical structures from the algebra alone, abstractly, with the programming language sort of following along. So this turned out to be kind of quite a bit harder to do, right? Partly because nobody really understands that well how to formalize mathematics. So there have been various attempts at that, but most of the effort that the people who developed Axiom spent had to do with how to apply abstract algebra to computation. And that was anyway.
Another big topic is artificial intelligence, using computers, of course.
Yeah, well, this is quite orthogonal to that. I mean, this is, using computers to do algebra, basically, in the most abstract way possible. And artificial intelligence is, I would say, almost entirely unrelated to that endeavor, right? I mean, it's this is saying something like, how should I?
Well, proof theory. How to, there are proof programs. I'm not sure what language they use to do that, but it must be related to what you're talking about. Proving software.
Theorem proving. I mean.
Yeah, theorem proving.
Yes, that is sort of like the logical branch of the abstract application of computers to calculation, right? So it's where you're concerned primarily with logic, and you can consider logic as a kind of a subset of algebra if you want.
Yeah, Boolean algebra, of course, would be that related.
But really, what I'm talking about is starting your computation with defining a ring, for example, so that you want to define a ring as involving two operations, something that's like addition and something like multiplication, and these operations have a relationship to each other, like they satisfy certain axioms, and provided they satisfy those axioms, you're willing to call them a ring, as an example of a ring, right? So this in Axiom, you start with the notion of a ring as a programming structure. You say, this is my ring. This is how I implement addition. This is how I implement multiplication. But the fact that it's a ring means that certain axioms hold. And the computer algebra system assists you. I wouldn't say it completely structures, it doesn't limit you to only satisfying these axioms, but stating these axioms up front, it is something like saying that you're working in the category of rings to start with, right? So that means you have certain formal structures that are present once you define what these operations are. Maybe I'm not.
Well, of course, I know in mathematics, always had difficulty programming non-commutative multiplication. So it wasn't, mathematics basically wants to make everything commutative.
Yeah,
but that's because mathematics is sort of fundamentally just manipulating symbols, right? It doesn't.
I remember one work that I was making with Mathematica, and this was to build an Grassmann algebra in this. And then we need to avoid the use of standard multiplication product and summation, and then we can build an non-commutative algebra in this. And now that Professor was speaking about the axiom, I remember that one of most interesting things in this way is that we need to define first, for example, if I want to build an Grassmann algebra, I need to define first products, for example. And then the definition of product needs to be in the most abstract way, most abstract way. And then in Mathematica, I think that we can think in operations like functions, like abstract functions that have one name and arguments. And this is an interesting way of defining. I try to use this way of building when I presented the idea of interaction. Because if we start with the idea of interaction in the most abstract way, we need to define first the existence of, suppose in an axiomatic way, the existence of interaction. And after, we need to define what are the arguments that are describing this interaction. And after, we define the properties in this, that is the building way that one can get new properties in this building work. Then I remember that I have some old files in Mathematica that maybe in a next session of the seminar I can present how those was built, because in the same way I was trying to make some things in the Frobenius problem, that in that time I remember that we was trying to build the observer algebra, observers.
Yes.
And
yeah, let me, okay. I wanted to get, before we finish, I wanted to actually show you some of the calculations that I did in this observer algebra, which is really what I wanted to talk about today. But
I was really interested in what Jesus has to say regarding programming Grossman algebra in Mathematica. So it'd be good if he can talk next time, I think.
Yes,
well, there's a very large package available for Mathematica, specifically implementing Grassmann algebra.
Yes,
Okay,
there's many.
There's in fact, an entire book published on the subject.
Yes, but I think that it is interesting to review the basic definitions that we need to use in this in building this kind of algebra.
Mm-hmm. Well, and this is sort of related to what Oshevich was saying about Clifford algebras, is that he wanted Clifford algebras to be presented in the most abstract way possible. That just from the axioms alone, without any reference to representations, and even with very limited very to not allow the notion of the what's the right word, the grade, not to allow the grade to enter so easily. So that was part of the reason why he was interested in Frobenius algebras, the Frobenius algebra structure of Clifford algebra. But so let me just back up a little bit, and then so what I was doing in Axiom at the time was implementing what was needed in order to do the kind of calculations that were discussed in Ostrevich's paper on operands, right? So considering we needed a way to represent this composition of operators. And so I ended up programming a package, a component of Axiom called just the linear operator package. And it was a means to actually implement these calculations. Like so you could write out the calculations in tensor notation, and they start to get quite complicated. But if you express them using this linear operator package, then you can read this this associative structure like directly from this command that's entered to Axiom. So in this command, we're taking the tensor product of these two operators, the multiplication with identity, and then composing it with the multiplication. So this is another representation of that same diagram that I showed earlier, right? Where we have something with three inputs and one output.
Excuse me, in this associator and in the past graphic that you presented, you define this in terms of three sets. We can say sets that are going inside in the operation after, but we have here not binary operations, but we have here a ternary operation. And then after you define this in terms of binary operations, that's right?
No, not necessarily binary. This is implementing directly Ostrevich's notion of grafting, right? So this is binary in this case because in this example, because we were just talking about some operator with two inputs and one output.
Yeah.
But this linear operator with two inputs and one output actually turns out to be exactly what you need to represent an algebra, right? It's if you think about how this linear operator would be represented, you'd end up with looking at the structure constants of the algebra. Right? So these structure constants tell you how to perform multiplication in the algebra. But at this point and at this level, we're only interested in the idea of expressing the notion of composition and grafting. We're only interested in grafting. And then the result of this ends up being represented should I write this in an abstract basis, right? So we end up with scalar expressions in some abstract basis, but this abstract basis is like the basis of a n by m tensor, right? So all of these graftings end up being tensor expressions with of the of the usual kind, but they end up being quite complicated in the end. I don't know. Anyway, so let me. There's nothing too exciting in here.
Yeah, I'm wondering whether the books you're talking about, Grossman algebra, are by John Brown. I just recently became familiar with his books. I don't
Yes, the
have
one
them.
who he's a book that is all about his Grassmann
Grossman,
package for Mathematica, right?
yeah,
Yeah,
Grossman
I
algebra.
think
And actually,
yeah,
there's 2 volumes. The second one he never quite finished, but someone, I guess, finished it for
mm,
him.
yeah. So it goes to a great length to show how Grassmann algebra can be applied geometrically, right? And that's most of most basically probably everything that you were discussing at most recently at the application of Clifford algebra conference uh, could be expressed equally uh, uh, using these notions directly from Grassmann algebra. Perhaps not
Well,
equally.
that's what exactly what I do. I have 2 compatible Grossman algebras is what I call it, and then that's the
Yes.
Clifford algebra. Simple as that.
Yeah. So the question is, well,
Yeah.
if that's true, why do you need Clifford algebra at all, right? You just that was the
Well,
argument that Oshevich had a lot of, over and over again, I think.
well, it's the applications in computer science where they have that dot product, which reduces the grade, and the wedge product, which increases. Those are very useful. And now, of course, you represent rotations as spinors by a two-sided representation of rotations, which is extremely useful.
But you see,
That's why it's,
with Grassmann algebra, there isn't a natural notion. Well, there is this notion of insertion or evaluation, right? But that requires that you have, as you say, 2 Grassmann algebras. Um, and it's a Grassmann algebra of vectors and a Grassmann algebra of forms. And then you can, this whole thing about the Frolicker and Ingenhouse algebra arises from this notion that you have a relationship between these 2 Grassmann algebras, um, so that you have a creation structure and an annihilation structure, right? And the annihilation part gives the scalar part, or can like the degree 0 part. But all of that algebraic structure can be presented abstractly as a way of producing this.
yeah, I just de-emphasize it. A covector is what just a mapping of vectors onto scalars, but a Clifford
But
algebra really is, like
but
I
the
say,
covector is essential to the notion of Frobenius algebra, and because the Frobenius algebra is defined by the covector, by this Frobenius form in relationship to the multiplication, right? So you take the multiplication of the algebra plus a covector, and that gives you the scalar product for that algebra. Right?
yeah, yeah, like I say, a matrix is not a covector. This or it's a linear operator. So a linear operator can be interpreted as a geometric number. Basically, it gives linear operators a geometric structure in terms of anti-commutativity and in terms of the notion of a idempotent. That's what relates the 2 Grossman algebras.
But write this, say this in a different way. Can you think of a natural way to associate a scalar product with matrices in general? Right? I mean,
Well, yeah, I think you can. That's exactly what the idea of
well,
this structure is.
but
I think.
the way you do that, right, is to take the ordinary matrix multiplication, and then you take the trace, right? So,
Okay, yeah,
right, and the trace of the matrix, it has a very special, intrinsic properties. Um, it
okay,
has a clear definition, unambiguous definition, even if you don't know the basis. If you don't, all you need are linear operators. right? So the whole point of this stuff that I was doing in Axiom was as Jesus said, was to keep this as abstract as possible, right? And so these are linear operators, but with, you know, based on some underlying ring which is unspecified, right? And
But of course, engineers and people that apply geometric algebra are not interested in just, they're trying to give a geometric idea of bivectors, trivectors, and everything has a geometric interpretation. So you try to, that's why it's called geometric algebra. Everything in the algebra is a combination of vectors plus bivectors plus trivectors and so on, which are elements of the Grossman algebra, of course.
Let me skip. Okay, so I'm going to change one last final subject. I just want to skip back to this paper, the beginning paper. Oh, where was this? Okay, this is the paper, the one that has. No, this is not the one. This is not this paper, but I think it's this paper. Yeah, let me just skip back. Yes, this is where we have the Frobenius algebra of two idempotents.
Now, what is that one? What is that algebra? Can you go to page 18? Let's take a look at it.
Yeah, yes. And so this is, first of all, in this paper, it's viewing the Frobenius algebra as a subalgebra of the Ningenhaus-Richardson algebra. So it's specifically the associative subalgebra of this larger algebra. And so the definitions, the reason why that's important is that tells you how to actually define the properties of these the Frobenius algebra, and just as in everything else I was talking about today, the important thing is that you need, in order to define a Frobenius algebra, you need this operation that has one input and no outputs. It's the sort of equivalent to the co-unit, co-vector, or trace, right? And this structure here, this is all about what is a Frobenius algebra. But ultimately, let's see. Just a minute. Let me skip ahead here.
Here's idempotent. Yes.
Yes. So first of all, you're interested in the subset of the algebra, the elements that are idempotent, but then in addition to that, they satisfy this trace property, right? That if you take like three of these elements, then you can reduce 3 to 1 because this relationship holds, right? That it tells you, among other things, that for a Frobenius algebra of a certain size has a dimension of 1 plus n squared, right? Anyway, let's see, where do we go here? Yeah, we have this co-algebra structure that we were talking about.
Okay.
And anyway, ultimately, Olszewicz in this paper was interested in finding out, like, what's the structure of this Frobenius algebra in the case of two generators, and you can calculate this in some detail. You end up with this matrix that you need to diagonalize.
Yeah, could you
Basically,
send me a copy of that paper when you're done with it? Or just,
sure.
just send it by email.
Yeah,
please.
sure. Okay, so what I wanted to do was to actually compute this result, which is what Oshevich had already done by hand for the case of 2, and extend it to 3 or 4 generators. That was my goal.
Okay.
And in order to do that, for reasons that I already was sort of talking about, I used a computer algebra package called Axiom, and this is the 9-dimensional Frobenius algebra. There's what Oshevich was talking about was the 5-dimensional one, and then we also extended it for 4. Some of the things I was talking about today, for example, about Axiom, for example, is sort of shown here that one of the first things we're doing here is defining this monoid, just generated by 3 elements. So a monoid is a very simple abstract structure. It's just a multiplication, abstract multiplication on those 3 elements. And so it ends up being, the words in this algebra are just strings over that alphabet, without any information on what those words mean, right? Without imposing any more structure. But given that monoid, you can generate a module, right? So a module is like a vector space over that way of doing multiplication, right? So ultimately, all of this is about using the axioms. Let's see, go back to this paper, like using, go back here. Using these axioms, for example, but implementing this as a quotient over the free module, so that this coding here has to do with implementing that that first rule involving the trace. So ultimately, you end up being able to this 3. How should I write this? These are the structure constants for the algebra that the Frobenius algebra represents those according to those axioms in the most abstract way. I'm getting to this part, yeah. And then ultimately we can just ask Axiom with a single command to generate an abstract algebra using those particular structure constants. And with this command, with this algebra, we can ask for a lot of, you can ask a lot of things about it. Like you can ask whether this is an associative algebra, whether it's a commutative algebra, does it satisfy Jacobi identities, etc. And then we can actually perform, use the multiplication in the algebra to evaluate expressions,
So it's a very general algebra, that's what you're saying.
Yes, it's completely general. There are no restrictions on what it is other than the restrictions that were placed on it because it's a subalgebra of the Frobenius algebra. And the whole point of this, though, was that these idempotents represent observers in relativity, right? And these idempotents arise. How should I say that? Well, they arise from directly from relativity. So applying Frobenius algebra is a way of representing the structure of relativity, and the observer structure of relativity is naturally associated. Sorry?
Each reference frame has an idempotent associated with it, I suppose.
Yes, and the idempotent property is because one observer looks his space in like how do you say repose space in rest.
Yes. At rest,
in rest.
Rest frame.
But one result here that surprised Oshevich was that I could, well, let's see, I'm gonna skip on here. We can, Oshevich wanted to know what was the center of this algebra. So in other words, it means what are the elements of this algebra that commute with all the other algebras, right? All the other elements of this algebra. And it turns out that there is only one, and it's the identity. But it's not the identity that you might expect. How should I say that?
Oh, what is it in terms of the basis of ABC or whatever it is?
Yes. So this expression here is what this identity, what this identity is expressed in terms of the P, Q, and R, right? Right, and then it's also expressed in terms of the binary combinations. And these constants in front are related to the mass and the gamma coefficient associated with each observer.
So that's also an idempotent, right? It's an idempotent. If you square that, you get itself back.
Yes. Yeah, that's, for example, that's what this says here. Well, this says that it's in the center, right? It says that we take this element C and multiply it by any other element of the algebra, and it's equal to doing it the other way around. So it commutes with everything. But this in itself, this element in the center is not in itself the identity, but if we divide it by the trace, then we do end up with an element that is the identity. So it's, anyway, we can carry this out. And now this particular set of calculations was extended later to include calculations for the center of mass of three bodies, because that was a subject that came up a lot, because this center of inertia can be expressed as a relatively simple expression in terms of these idempotents. And in the papers that Oshevich had published, he had done this for the case of two idempotents. But it wasn't immediately clear how to extend it to 3 or to 4. And so that was one of the things that I did later. But the first part of this calculation was just setting up the algebraic structure. And then once you have the algebraic structure in place, then you can actually evaluate all of these your more interesting
You
questions.
can't do anything by hand. It's just too complicated.
Very complicated. Yes, like it.
Who would want to do it by hand?
Well, yeah. I mean, for the most part, you want to spend your effort, on the conceptual side of it. Let the computer do the work. And the problem is that doing this by hand, it's so easy to make a mistake. Like you may
Yeah,
drop
exactly.
one
That's
minus sign and everything is ruined, right?
That's like Clifford algebra was the same way. It's impossible to do hand calculations.
I found there some things that I don't understand, because I found there some conceptual problems that I was discussing with Professor Algebra many times. But if we extend the number of observers, then we finally find one number of observers that describe all the system. Because if we are thinking about one four-dimensional space-time, then finally we need only 4 observers for describe all the events. And then this is a problem, because then if we think about one mass center of these 4 observers, then we need another observer that is looking at mass center. And I think that there are
but see, I don't think that's the case, right? Because, like, for example, this expression here for the center of momentum, right, is given only in terms of the 2 operators, of the 2 observers, or 3 observers in this case.
But then there is not sense about the mass center between 2 observers.
Well, the sense of it is that this is another virtual observer, right? So if we have 3 observers, then there is one more virtual observer, which is the observer which is associated with the center of mass, right? And this can be defined in terms of the 3 observers.
Because I think that this, if we think in this way, this takes to us to the Minkowski space. And then it is present the problems that we have 1 0 for all the rest of the observers. Then I think that this is there is a problem in this implementation, because we cannot go in an unlimited way, building more observers. If the space-time have are the finite dimension. Okay, those are problems that I was.
Well, I think I know what you mean, but you see, this algebra extends naturally to 4, right? So I can do these calculations up to 4 observers. If I do 5, then it takes the computer like several days to come up with an answer, right? But the mechanism is still the same, right? The underlying structure is still remains well defined. But just before I finish, let me show you that there was one other way. This was using Shevich's notion of Frobenius algebras, but you can do the same thing. Just let me just take this. Which one? Idempotent observers, yeah. So this is doing the same calculation, but with representation in Minkowski space.
Okay.
So we have the same types of calculations. I think but now the algebra is sort of implemented directly in terms of its representations, like as 4 vectors. But ultimately here, there's other things.
Each rest frame corresponds to gamma 0 as in the Dirac algebra.
Well, each rest frame corresponds to specifying a 4 vector. So you specify one 4 vector, that's one massive body. You specify another 4 vector.
But it has square 1, right? It has square 1. Well, depending upon the signature that you're using. Or you can make an idempotent out of it. It has square 1, then of course you can make the idempotent out of 1/2 1 plus that gamma 0 then.
Yes. Let's see, where do I describe that? Okay, so we just take an arbitrary 4 vector. That's what this is doing here. And then
Okay.
in fact, we wanted at least 2 of them here. So or 3, I guess. And then this is all about talking about relative velocity, etc. But then this construction here is the construction of the idempotent associated with that observer. So we take the tensor product really of these 2, or I think you call it Kronecker product, and then you can show that this is in fact this matrix, right, is idempotent matrix. Anyway, we do this.
It's a primitive idempotent. It's a primitive idempotent.
Primitive idempotent, yeah. And there are also nilpotent operators. In this formalism, the nilpotent operators represent photons, as the idempotent operators represent massive bodies or observers. So there was a question about how do photons enter into this whole formalism. That was interesting. But where do we go here? This goes on and on for a long ways, lots of calculations, but ultimately end up calculating momentum the same way, right? Like by using the same formula, but instead of doing it abstractly, we're doing it in terms of this particular representation. And so this is just showing that this particular construction up here, which is a little bit hard to read, but it's equivalent to what I wrote in the other calculation, but it ultimately ends up being that this matrix M calculated through this relatively complicated thing also turns out to be an idempotent. And it has the correct trace, right, for it to represent an observer.
And what is the trace? What is the trace?
The trace is just the sum of the diagonal elements of this matrix. Right?
It's not a value, though, not a particular value.
It's a value of 1.
Okay, it's 1. Okay, exactly.
Yeah, yeah. Because of the construction above, that says that a massive body is represented by this particular matrix, that construction has, among other things, the property that its trace is equal to 1.
Yeah, it's a primitive, so it's just, like you said, 1, 0, 0, just 1 in the first place and the zeros everywhere else. Then.
Mm-hmm. And I think I did the calculation. This is the same thing, doing it for 3. I mean, you just get larger and larger expressions, and it takes longer and longer to calculate these things, but ultimately they end up
you get 1
satisfying the same rules, right? So this one is, again, it's idempotent.
Why do you have zeros there? That's all right.
Yeah. So anyway, so we also have this notion of orthogonal idempotence, right? That arise because we have a natural notion of identity.
Or mutually annihilating idempotence, the same thing.
Mm-hmm. Yeah, I didn't have, in this particular calculation, I didn't go into the, well, no, I guess I did. This thing called n here is the center of the algebra that was calculated in the previous calculation, but calculated abstractly in the previous one, but calculated using this equivalent formulas, but in the representation for space-time. And I don't see here uses any reason that this construction is somehow limited, because its representation is in Minkowski space. It doesn't. There's nothing sort of like naturally limiting in that representation. So this was sort of a negative answer to Lashevich's question. I think was that he wanted to say, in a sense like you, that if we have enough observers, we don't, then we know the structure of space-time, in a sense, right? That,
yes,
so in the sense that we don't really need any more observers, right?
And then there is a privileged observer that have the 0 of this representation.
Well, there is a privileged observer that is the center of inertia of a given set of observers. This observer is not a real observer in a sense, right? But it satisfies all the algebraic properties required of observers, right? So that we're free to choose this center, just like we're free to choose, the center of the solar system as being not quite the center of the sun, and if we do that, then everything has a nice simple binary structure, and that's where Oshevich was going with this. I think that once you are able to define the center of any given set of objects, then you express their interactions always just with the center, just as you would classically, right?
But if we go to the idea that observers are in a category that is a groupoid, then there is no way to get a 0 for those for this category.
No way to get a
To get a common zero for those
common zero
of this category. Yes. Mm-hmm.
Hmm.
Mm-hmm.
Well, I mean a common zero velocity, right? There is no common zero velocity.
But then this means zero velocity for one privileged observer, right? I have many problems with these ideas because algebraically we need to be strict in the way of if we think in a groupoid category, then this present to us restrictions about the operations that we can implement in this. And I think that is.
But see, in the Frobenius algebra formalism, this observer algebra, relative velocities are always products of two atomic things, right? So if P is an observer and Q is an observer, then their product, PQ, is the representation of their relative velocity.
For whom? For who? For who?
For the pair, right?
No,
The velocity of Q relative to P, right?
My idea is that Q is seen is not possible, is not equivalent that P is seen.
Could you repeat that? I don't.
Okay. My idea is that if we have two observers, P and Q, the observations are not translated from one observer to another. If we don't add some axioms that is about, for example, the constants of velocity of light. And then in this way, we can make, we need to add the concept of information and translate information between them. And in these principal axioms is that is permitted to us to speak about the observation, the equivalence of observation between these two. But then if we speak about the observation of a third object, then we can speak about the relative velocity of this object.
Okay, I think I know how to answer that. I mean, because in discussions with Ashevich later, like most recently, he often objected to the use of the word observer. Like he said, don't use this word observer. Don't call this observer algebra, right? Because it really has nothing to do with observation, right? That when we define the relative velocity between two massive bodies, this is a physical property of the universe. It's not a matter of one thing observing another. it's a physical relationship between two things, and this physical relationship between two things exists independently of observation. Right? It's just like
what happens if you change the mass with a charge, say moving two charges in different reference frames? Does that have a center of mass too?
well, charges. As soon as you have charges, you're talking about dynamics, like of some sort, right?
Well,
so you're talking about but you're as soon
dynamics
as you
too.
like if you're talking about charges and you're saying you're interested in how these things interact, but and that I have to agree with Jesus that as soon as you need to start talking about interactions, this is the subject gets more complicated.
But of course, two masses have gravitational attraction, so it's dynamic too, just in the same sense.
But from the point of view of relativity alone, right, without even thinking about whether things are interacting or not, I mean you just have like two separate parts of the universe, two massive objects, right? And these two massive objects, at least in Noshevich's view, have a relationship to each other that we call their relative velocity. Right? And we represent each massive object abstractly as a four vector in Minkowski space. And then the relative velocity is given by a relatively simple formula that comes from the structure of the hyperbolic structure of Minkowski space. And but we don't need to do any observation, right? It's just that Q is related to P in this particular way, right? Once we know what P and Q are, right? Now, we do want to say that this has something to do with observation, though, like that, and I agree that gets a bit more complicated. But you can have the kinetics.
Inertial mass is the same thing as gravitation. Is equivalent to mass, actually. Inertial mass is the same concept, really. Supposedly in general relativity, of course.
No, in general relativity, in the current, formalisms in general relativity, the concepts of inertial mass are conflicting. Like there are a number of different definitions of center of mass that are seem to be appropriate in different cases, but in every case, this center of mass property is a structure of the system as a whole, right? It's a non-local thing that doesn't.
So is there an answer to that question? What I guess there is.
Yeah. Well, Shevich said there's an answer to this question provided that you're willing to change the definition of what you mean by relative velocity.
Oh, okay. Yeah, that goes into that.
So if you accept this notion of relative velocity as a binary thing, as just a relationship between two things, if you accept that, then you can compute something that is equivalent to center of mass.
Has anyone reacted to these ideas, or has anyone reacted?
Jesus perhaps is saying something counter, right? He's perhaps saying that he's not entirely convinced that we know what we mean by relative velocity unless we have an outside observer.
Yes, because for me, PQ is the relative velocity that P looks observing Q. And QP is the relative velocity that Q sees observing P. And those are not related.
Well, but see, this is connected directly to this notion that Dr. Sopcich you asked about a few times, is that whether we need three bodies in order to define relative velocity, or
Okay.
just two, right? So if we have it's true what you just said, Eustace, that if you accept that relative velocity is a ternary thing, then we can say that the three bodies are P and Q, right? So we can say this is P observing Q as P, right? And so this is this is a ternary velocity concept, right?
But maybe we can think in this way: P, Q, and the photon.
But the photon doesn't produce.
Interchange.
The problem is that photons don't define reference frames, right? There's no motion relative to the photon.
But we think that the photon has an absolute velocity.
Well, or more abstractly, we think that a photon is a nilpotent operator, right?
Okay.
Whereas a massive body is an idempotent operator.
Yes, but then the problem is that the observer has PQ, and they use a fundamental property of nature, that is the velocity, the absolute velocity of photon. And this makes the necessary elements for building this algebra.
Yeah.
Well, I think I have some tools here with this computer algebra system that can explore this structure, this question of how do such nilpotent operators representing photons, how do they relate to idempotent operators?
Well, I think I have the answer to that. An idempotent is the product of two nilpotents. That's why I define this relationship between these compatible Grossman algebras, which is why I'm interested to see what Dr. Cruz would have to say about Grossman algebras. But I think if you define the idea of compatible Grossman algebras, that's just two nilpotents is an idempotent. And the simplest example is taking the matrix 0, 1, 0, 0 and 0, 0, 1, 0, just off diagonal. And the product of those two is an idempotent.
So does this somehow suggest in physics that each massive body is associated with two photons?
Well, exactly. You could think about it that way. What these matrix 0, 1, 0, 0 and 0, 0, 1, 0, that represents two different idempotents. And if you make the product of it, you get the idempotent 1, 0, 0, 0, the usual for 2 by 2 matrices. Now, of course, if we're dealing with 4 by 4 matrices, well, that's the thing. That's I think any matrix can be written in terms of products of nilpotents, and that applies to Minkowski space-time. In fact, I show how to do that as an example. But anyway, maybe Dr. Cruz can talk about Grossman algebras, and we can proceed further with that idea.
Yes, yeah. Let's okay. Let's do that in 2 weeks' time.
Okay.
I'd also be interested in seeing what you have done in Mathematica to represent this algebra.
Yeah, I like to. I don't really want to buy Brown's book or even adapt his way of looking at it. I'm interested in it.
No, okay,
Yeah,
but I need to advertise to you that it is an old work. I don't
Yeah.
remember. And
That's
then
no problem. I feel exactly the same way. And so when I sat down to look at these calculations, I discovered that they were done in 2011. And when I looked at it, I thought, I I only partially understand why I did this. Right? It's almost as if it was done by someone else.
well, I
But
understand the feeling.
then when I was going to give my talk, 2 weeks ago, I sat down to this computer algebra system that I'm showing you here, and I discovered that it no longer worked. that that in fact, in 10 years have gone by, and the axiom system has actually been changed subtly. And so when I said to redo these calculations, everything was failing, and I thought, wow, this used to work. What's wrong? So then it's like every time you get a new version of Mathematica, you have the risk that maybe something that you were doing before is not working anymore.
Yeah,
Because
that's awful.
something, well, yeah, it can be awful because it means that you have to go through the whole process again to remember what it.
Yeah, write it over
yeah,
again.
maybe,
Yeah.
maybe. But
And hope.
also I like to present this in 2 weeks.
Okay, great. Um, Thanks very much for showing up and dealing with my sort of frustrating presentation. I hope it wasn't
No, it's very
too
interesting, and I
confusing.
look forward to Dr. Cruz's presentation in 2 weeks.
Part of the problem always, I've tried to do this a few times, and I think I'm sitting in front of these calculations, and I think I know exactly what they mean and why I did this now. But the problem is to express it to someone else. Like, and it, I don't know. It's, I guess, if you're, it's a problem all the time, but it seems to be worse when you're dealing with computer algebra, because when you sit down in front of your calculations, you're using certain tools and you're making certain assumptions about what you represented and why, and to express that to someone else takes a very long time. Like it takes more than just a 1 hour or 2 hour seminar. And I've never found a way of solving that problem, except when I can make the computer algebra as close as possible to the mathematics. So then you say, well, this odd looking thing in the computer is this particular mathematical structure. And you only have to convince people of that. And then in principle, they can understand the rest of your calculations. Um, and that was one reason why I was much more interested in Axiom, using Axiom when I could, was because it took this view that what the computer is doing is really mathematics. It's not just switching the order of symbols and like adding another connection between them and so forth. And one of the problems with Mathematica and Maple is that it's much harder to make the calculations look like mathematics. It's like um, that's just my sort of point of view that I developed over time. But I still use Maple and Mathematica and Maxima and several other computer algebra systems. But I keep going back to Axiom when I can, right?
You just have to document your steps in your Mathematica. You have to explain at the side what you're doing.
Well, I liked what you did in one case, Dr. Sobchak. You put some Mathematica code as an appendix to your paper. So you have the paper presenting the mathematical argument, and then say, here's an appendix, and this you should believe me that
Yeah.
this appendix is useful to understand this mathematics, right?
Yeah, I presented some ideas in a mathematical international mathematical symposium organized by the Mathematica. I remember this was in Banff, maybe in 2003. I presented that. And there is some expressions that built in Mathematica there. I am going to look about this work because maybe it's a good starting point for the presentation.
Okay, great.
Mm.
Okay, well, I'll see you in 2 weeks' time.
Okay, thanks a lot.
Okay, I'm looking forward to it too.
Okay, bye.
Bye.
Bye-bye.